Hello everyone. So I'm Leo Kingston. I'm working in Poland, Division of Dynamics, Łódź University of Technology. So today I'm going to talk about some extreme events in non-linear dynamical system. So this is my outline of talk. So first I will explain something about the concept of extreme events, and then what are the reason behind in it for these extreme events. Then some routes to extreme event, like what are the routes to chaos, like that things. Then some what are the interaction between the extreme event formation, and finally conclusion. So as you know, nowadays we are living on so many extreme situations of nature and so many things. For example, the huge flood and heat waves, droughts and cyclones, and this nuclear plant disaster and share market crisis. So I can tell you a simple thing. So what happened in very recently in India, in south part of India, so according the meteorological department, according their rule book, so they said it's a red alert for for that particular regime. So the maximum limit for red alert is about 32 millimeter rainfall. But what happened? That unexpectedly there was up to 98 millimeter rainfall. So which creates some disastrous consequences. So which means so we need more and more understanding to prevent the people and society against this kind of catastrophic events. So dealing with this natural data is still difficult because some data are missing. So recently people working on some complex dynamical system data to understand or predict more on these extreme event things. So that is our focused area. So far we understand that. So there are some instabilities involved in these extreme event formations. So that are all called dynamical system definition as instability in periodic motion. Suppose if there any some suppose let's consider a situation. So we have some periodic steady motion. If there is some burst occurring in that from periodic motion, then we call it as a Pomi-Manuvale intermittency. So this is introduced by Pomi-Manuvale. In other case, if there is some instability originated in quasi-periodic region, so you know there is a clear difference between periodic and quasi-periodic. So then we can call it a quasi-periodic intermittency. So in some other case, it can happen from the chaotic dynamics. So this is due to crisis-induced intermittency. So apart from that, there are other intermittency or instability also happen in non-dynamical system. So that are due to this attractor Huffing dynamics or instability in phase and antiphase synchronization manifold. So far we understand that these first three instabilities are very predominant in instability for origin of different extreme event in dynamical system. So these are some examples. So the first one is let's say it's a force linear system. I will discuss more later slides. So here see the system is most of the time in the bounded chaotic regime, but occasionally there is some bursting. So in order to confirm this dynamics extreme, so we are using some statistical definition. So that is nothing but significant height threshold. So here we are using this mean plus 4 to 8 times of standard deviation. So this is this rare event appearing from the bounded chaotic motion. But if you see here, this is some coupled neuron model. So this is basically periodic dynamics. So from that, there is some occasional bursting occurring in this model. So similarly, this is a laser model. So this dynamic is quasi-periodic. So the occasional bursting appearing from the quasi-periodic motion. So now I detailedly explain about a simple model that is called force Liénard system. So this is similar to Duffing oscillator, the well-known Duffing oscillator. So this is a two-dimensional periodic forcing model, and it's look very simple equation, but it gives more complex dynamics. For example, this is a bistable system. So means in this figure A, this white region represent dissipative region, whereas this outside is conservative region. So if you choose any initial condition inside this white region, it will converge to this stable fixed point. So here there are three fixed point. This is stable focus, and this is unstable focus. This is, sorry, this is stable, this is saddle, and this is unstable focus. So if you choose in initial condition, whenever it will settle into here. Suppose if you choose any initial condition outside this white region, so it will create some neutrally stable orbit because of the conservative nature of the system. Once you introduce the periodic forcing, what happened? So this white region is expanding. So if you choose any initial condition in this either white or in this gray region, so we will find these extreme events. But if you choose outside, so it will create some quasi-periodic motion. So this is the time series of for these dynamics. So means most of them it's in the chaotic motion. There is some occasional expansions. So as I mentioned earlier, so there are different routes to extreme event. So the first one in this model exhibiting crisis-induced intermittency. So first I will explain what is intermittency, what is crisis. So as you know, the crisis is sudden disappearance of the chaotic attractor. So let's say here, if I change the forcing frequency gradually from 0.8 to the lower value, so the system exhibit the period doubling route to chaos. When it reaches the critical parameter value, there is a sudden expansion. So why? Because of the chaotic trajectory moving closer and closer to the saddle orbit. So as I told earlier, the system have saddle point. So once you introduce the forcing, the saddle point becomes saddle orbit. So whenever the trajectory touches the saddle orbit, there is a sudden expansion. So which is clearly here. The rare event have very less probability, but this is due to this bounded chaotic region, we have very large, higher probability. So next, the similar system exhibit another route also. So which is from period to large expansion. So it's clear here. So the system in a periodic state. So whenever it approaches the critical point, there is a occasional large expansion from the periodic motion. So which is confirmed by the distribution. This is quasi-periodic intermittency in Zeeman laser model. So this is a 7-dimensional some complex model. So basically the system initially the system in a periodic state. So that's why the Liénard exponent is in negative. So then it turned into the quasi-periodic regime. So the 2 Liénard exponent is in 0. Then it turned into chaotic attractor, which is this is quasi-periodic, which is confirmed by return map. So there is a closed orbit. So here we can find some extreme event from the bounded quasi-periodic region. There is occasional large expansion, and and we are confirming with the distribution. So this is not just numerical observation. So we confirm this appearance of extreme in electronic experiments of this Liénard system. So for that we just create some analog circuit for this Liénard model for a proper value of this forcing frequency. So the system shows the chaotic, and there is occasional large expansion from chaotic motion, and this is from periodic to occasional large expansion, and its corresponding PDF also showing that the rare event have very less probability. So now the question is, so what is the effect of time varying parameter? So let's consider, so if you are measuring, if you are doing any experiment in a laboratory, so the parameter value of the system can change in many factors. For example, the temperature in the room temperature can affect the system condition or something like that. So we have to carefully analyze this kind of phenomena using this time varying effect. Let's say, so here I am choosing my parameter value here, means in bounded chaotic region. When I introducing the time varying forcing parameter, so means I am introducing this slow frequency forcing in the one of the system parameter. So because of that, if I varying slowly this frequency, so in this case also the system exhibit extreme event. So we have to very careful about this time varying parameter effect. So here the system is exhibit chaotic then extreme event, and further it will show more large expansion. So we can't say this is extreme event because as per the definition, the extreme event should be a rare event. So we just discriminate the three different dynamics. So this is bounded chaotic region, and this is extreme event, and this is large expanded chaotic dynamics. So as we can see the distribution, the rare event have very less probability, and also we find the inter-event interval distribution, which means we are finding the interval between two successive extreme event. So which follows Poisson-like distribution. So means it's very difficult to relate the consecutive extreme events. So now then we extend this study into the coupled oscillators. So in this coupled system, so we are using some time varying interaction. So as we know, the interaction between the two systems cannot be static for all the time. So that's why we are using some step function to see the influence of the system. So let's say for a particular value of the system parameter, and if you are changing the this time varying parameter value, so in this case also we can find this unusual phenomena in the dynamical system. So this is the time series of extreme event, and this is the corresponding distributions. So here we are fixing the system parameter, and we are choosing three different duty cycle values. So means we are choosing three different interaction values. So we can clearly see, due to this different duty cycle value, there is a enormous shift in the transition point. So which means this time varying parameter play a crucial role in the extreme event formation. So which is confirmed by some two-phase diagrams. So here we are varying the control parameter value, and this is interaction. So for a different interaction timing, so we can see some significant change in the system parameter, the extreme event formation. Basically, this yellow region represent the extreme event region, and this is the non-extreme event region. Additionally, if you choosing the appropriate control time varying parameter value of this time varying interaction time and interaction parameter, so we can control the extreme event. So in this case, we fix the system parameter as a extreme event regime, but we are changing the interaction time as well as the interaction parameter value, so we can mitigate the extreme event in an appropriate region. Now the question is, okay, this is so far we have explained everything in as only a specific model system called Liénard system. So now the question is, so is it true for all other system? The answer is yes. So in order to confirm that, we took a neuron model. So this is called a Fitzgerald model. So here also we are using this time varying interaction parameter value h of t. So here the system exhibits some period doubling route to chaos, then large expansion. So this is some threshold value to confirm these rare events. So we can see there are some extreme events here. So sorry. So after using a specific control parameter, so time varying parameter value, so we can completely eliminate the large expansion. So which we confirmed in the two-phase diagram. So in this particular region, we can completely eliminate the large expansion. So this is not only applicable for a single coupled system. So we check this for a network of oscillator. So here we took 20 oscillators. So this is before control, this is after control. So we can, using this time varying parameter, we can effectively control the extreme event. So after the transient, so the system is complete, the rare event is completely eliminated because the maximum value is 0. So we have studied different routes to extreme event in linear system. So we have studied the impact of time varying parameter and time varying interaction in the system. So this is a common phenomena for a wide range of coupled oscillator and network of oscillator. And this is my collaborator, so Professor Tomasz Kapitaniak and Professor Shamal Dana and Dr. Suresh and Marek Walczak, and I would like to thank National Science Center Poland for the financial support. And these are our some of recent reports on extreme events. So those who are interested, you can read it, and if you have any queries, so you can write me. And thank you very much for your kind attention. And question, please.